Hello, my name is Jaylee Helskamp, and this is the first video from the Mathematics and Billiards group. In this video, I'm going to be talking about billiards on a rectangular shaped table. I'm also going to do an example of a construction, the proof for why it works, and then we're going to discuss why it's the shortest path possible and what would happen if we were bouncing the cue ball off an infinite number of sides. So let's begin. For this video, we're going to be working with the basics of pool. By that I mean we're not going to be hitting the cue ball on the side to cause it to spin, because when you do that, the path of the ball becomes less predictable. Instead, we're going to pretend we're hitting it in the dead center of the cue ball and bouncing it off a side, because when that happens, you get an angle of approach, which is congruent to your angle of departure. And this is true because the law of reflection. Now, I wish I had a pool table to show you that this happens, but I do not. So you are just going to have to take my word for it. But knowing that fact might come in handy for you one day. Maybe you're challenged to a game of pool. You could easily hustle the people because you know that fact. You can construct your angle of approach using the side of the pool table as one of your rays, and then your pool stick as the other ray. So you physically have your angle of approach, and then you can visualize your angle of departure and therefore the path of the cue ball. So you're welcome. I'm going to do a construction, but I'm not going to construct congruent angles or anything. I mean, I will indirectly, but I'm not going to do a construction of the path of the ball by using that fact solely. I'm going to use reflections because I want it to bounce off of multiple sides, and if I was just constructing a bunch of congruent angles, that would get dicey and not be as efficient as using reflections. So reflections are a middle school concept, really. You should be doing reflections in elementary school, middle school, and then our reasoning for all of this is kind of a high school level. But let's begin. So say we have this cue ball and this target ball, and we want the cue ball to hit the target, but bounce off of this side, and this side before it hits the target, because let's pretend there are a bunch of balls in the way, and we don't want to hit them. So how do we do that? Well, we would use reflections. We're going to take this cue ball and reflect it off of the first side and get our first reflection point. From there, we're going to take that point and reflect it over that second side where we want it to bounce off of. So when we reflect it over, we get that point. And finally, we're going to reflect that reflected point, and we're going to reflect it over our third side. So we have 3 reflected points for 3 sides that we want to bounce off of. From there, we're just going to create a bunch of segments. So we're going to connect that final reflected point to the target, and that gives us an intersection between the side of the pool table and our segment. So that would be your final bounce point. In this case, it's our third one. From there, we're going to create a segment with that final bounce point and that second reflected point as our endpoints, and once again, we get an intersection between the side of the pool table and our segment. And that's our second to last bounce point, or in this case, our second bounce point. I bet you can guess what we're going to do next. We're going to create another segment with our reflected point and our bounce point, and once again, we have an intersection, which ends up being our first bounce point. So we have 3 bounce points and the path that the cue ball would take. So if we hit the cue ball in the center and it goes on this path, it will end up bouncing here, here, and here before hitting the target ball. Very cool. So now we know how to hit the target, but why does this work? We can show how it works by doing an informal proof, kind of. So I already did the construction for hitting this target by reflecting this cue ball over this line and getting this reflected point. I'm only doing 1 bounce, but if you did multiple bounces, you would just basically extend this proof and repeat it a few times. But if we connect this cue ball to its reflected point, something cool happens with this reflecting line. So this reflecting line actually becomes the perpendicular bisector to this line. And bisector means it basically cuts this segment into 2 congruent parts. So this leg right here is going to be congruent to this leg. And when I say leg, we have a green triangle up here and a white triangle down there. So that's where the bisection comes from. But then we also have perpendicular. This segment is going to be perpendicular to the reflected line. And what that means is a right angle is formed between the two lines. So additionally, that angle is going to be right, but then this one's going to be right too because they're supplementary. So we have two right angles and two, therefore, right triangles. So we have a leg and an angle being congruent to the corresponding leg and angle, but we also have a shared side, and since this side is shared right here, it's congruent to itself, of course. So we have a congruent leg, a congruent angle, and a congruent side. Side, angle, side of triangles proves that these two triangles, the green one and the white one, are congruent. So since these two triangles are congruent, we know corresponding parts of congruent triangles are congruent. These two angles up here correspond to one another, so they are also going to be congruent. My congruent marks aren't very good. There we go. So those two angles are congruent. We can take it a step further and say that this angle is congruent to this angle because they are vertical angles in the vertical angle theorem. So by the transitive property, this angle is congruent to this angle. Well, if you look, that angle is the angle of approach, and this angle is the angle of departure. So by using our reflection method, you are getting congruent angle of approach, an angle of approach, and an angle of departure. So that does show the path that the cue ball will be taking to hit the target, which is very cool. Now we can say that this is the shortest path taken, and we can explain that using the triangle inequality theorem. So I have a construction here from Marcinick from CMU. He basically did what we did in our first example, but he started with the target ball, which is basically the same thing. So the path of the ball is shown by all these different colors, and that just shows us that this dotted line here gives us the path that the ball would take. So these two yellow are congruent, the greens are congruent, and the reds are congruent. This is just the path of the ball. So say instead of bouncing there, where that point we get from reflecting, we move the point over there. So the path instead goes here and then would follow the yellow, green, red. So this shape is the path of our ball. Instead of this dotted line, it becomes this path, the yellow, green, red. If you look, we created an obtuse triangle here. So we know that this new path is going to be longer than our original dotted path because of the triangle inequality theorem. And that theorem states that the sum of the two shortest sides of a triangle must be greater than the longest side. So the two shortest sides is this black one and then the yellow one. So these two, the sum of those two must be longer than the dotted one. And overall, this just shows that this new path is going to be longer than the other one. So we know our reflection method gives us also the shortest path. Now, say if we hit the ball and it had no friction and just kept bouncing off the sides. So bouncing off the sides an infinite number of times. If that happened, you can kind of see here, but we would get sort of a lattice pattern to it, because we would just get sets of parallel lines. This line is actually parallel to this line, and this line to that one. So that would keep happening over and over again, and you would get this lattice shape, which is really cool. So that's what happens on a rectangular shape table. And in the next few videos, you're going to see what would happen on an ellipse-shaped table. So thank you for watching.